Hello students, I am Dr. S.B. Nahire and today we are going to understand the concept of defect perovskites. Now let us look at the slide carefully. First point, high-tech materials are advanced functional materials. This means these materials are specially designed for specific properties like energy-related applications, magnetic behavior or electronic conductivity. Next, the term perovskite comes from the mineral calcium titanate, CaTiO3. This structure is very important because it represents a large family of materials with general formula AbX3. Please focus on this AbX3 structure. Now let us understand each site one by one. A site. This is occupied by a larger cation. It sits in a large space called a cubo-octahedral void. Examples include calcium, barium, and lanthanum. Now B site. This is a smaller cation. It is located inside a rigid BO6 octahedron. This octahedron is formed by 6 oxygen atoms surrounding the B site ion. Examples include titanium, copper, and iron. Now X site. This is usually an anion, mostly oxygen. These oxygen atoms connect the octahedra and form a three-dimensional network by sharing corners. Now look at the diagram on the right side. You can see the 3D structure where the B site is inside the octahedron and oxygen atoms are forming the framework. Very important point. Real materials are not perfect. There are always some defects or deviations in the crystal lattice. These imperfections are called defects. And interestingly, these defects actually improve the properties of the material. That is why we call them defect perovskites and they show superior performance. So remember this key idea. Perfect structure is ideal, but defects make materials more useful. In the next slide, we will understand different types of defects in detail. Now let us understand the next concept, types of defects and oxygen vacancies. First point, defects emerge when the ideal stoichiometric ratio is disrupted. This can happen due to vacancies, interstitial atoms, or cation substitutions. In simple words, when the correct number or position of atoms is disturbed, defects are created. Next point, these defects can occur at the A site, B site, or X site. And because of this, the local charge balance and crystal symmetry are strongly affected. Now pay attention to the most important line. The most critical and common defect is oxygen vacancy. This means oxygen atoms are missing from their normal positions in the crystal lattice. Next, when oxygen atoms are missing, the nearby BO6 octahedra become distorted. At the same time, the electronic distribution of neighboring atoms also changes. This directly affects the electrical and structural properties of the material. Now the formula part. The general non-stoichiometric formula is A1 minus X, B1 minus Y, O3 minus delta. Here, X, Y and delta represent the amount of defects present in the structure. Now very important concept. To maintain electrical neutrality, cations adjust by changing their oxidation states. This is called mixed valency. For example, a metal ion may change from +3 to +4 state. Now look at the diagram on the right side. You can see that when an oxygen atom is missing, it creates an empty space. This empty space acts like a pathway for ion movement. That is why we say, oxygen vacancy creates a pathway for rapid ion migration. So remember this key idea. Oxygen vacancies are not just defects, they actually improve ionic conductivity. In the next part, we will see how these defects affect structure and stability. Now let us understand structural distortions and stability in perovskites. First point, perovskite stability is dictated by the Goldsmith tolerance factor denoted by T. This factor relates the ionic radii of the constituent ions in the structure. In simple words, It tells us whether the ions fit properly in the crystal lattice or not. Now next point, if the value of T is equal to 1, the structure is ideal cubic. But if T deviates from 1, the BO6 octahedra start tilting. And this tilting causes large structural distortions in the crystal. Now understand the next line carefully. Defects further reduce the symmetry of the crystal. Because of this, the structure can change from cubic to other forms like orthorhombic, tetragonal, or rhombohedral. Now next important concept. These oxygen-deficient pathways created due to defects lead to very high ionic conductivity. This means ions can move more easily through the structure. Next point. If the vacancies are highly ordered and periodic, they can form completely new structures. One important example is the brown millerite structure, which consists of alternating octahedral and tetrahedral layers. Now look at the diagram on the right side. You can see the comparison between ideal cubic structure and distorted orthorhombic structure. In the ideal case, the octahedra are perfectly aligned. But in the distorted case, they are tilted, showing the effect of deviation in tolerance factor. Now very important exam point. Tolerance factor determines the basic crystal structure, but defects determine the actual functional properties of the material. So always remember, structure comes from geometry, but performance comes from defects. In the next slide, we will study how these defects affect electronic properties. Now let us understand electronic and physical properties of defect perovskites. First point. Oxygen vacancies introduce localized energy states into the band cap. These act as active charge carriers and help to increase electrical conductivity. In simple words, missing oxygen atoms create extra energy levels that allow electrons to move more easily. Next point, transition metal ions at the B site show mixed valence states. For example, iron can exist as Fe3+ and Fe4+. Or manganese as Mn3+ and Mn4+. Now understand why this is important. Because of these two oxidation states, electrons can move from one ion to another. This process is called electron hopping. Next line. This dual state allows rapid electron hopping between ions and sometimes leads to a phenomenon called colossal magnetoresistance, or CMR. Now next concept. These materials show strong anisotropy. This means their properties depend on direction. So behavior changes depending on which crystallographic direction you measure. As shown on the left side, anisotropy simply means direction matters. Now coming to thermal behavior, oxygen vacancies increase lattice vibrations. Because of this, phonon scattering changes, and properties like heat capacity and thermal conductivity are affected. Next point, defects also change the rigidity of the lattice. This means they affect how stiff or flexible the structure is. As a result, the elastic constants and mechanical strength of the material also change. Now look at the diagram at the bottom. You can clearly see electron hopping between Mn3+ and Mn4+ ions. This movement of electrons increases conductivity. So remember this key idea. Oxygen vacancies and mixed valence together improve electrical and physical properties. In the next slide, we will study preparation and characterization techniques. Now, let us understand the preparation and characterization techniques used for defect perovskites. First, solid-state method. In this method, we mix metal oxides or carbonates, then grind them properly and heat them at high temperatures. This process helps in forming the desired crystalline structure. Also, by adjusting oxygen pressure, we can control or tune the number of oxygen vacancies in the material. Now next, wet chemical methods. These include sol gel, co-precipitation, and hydrothermal techniques. These methods are performed in solution phase and allow better control over composition. Now, important point. Advantage of wet methods. Wet methods give better homogeneity, which means uniform mixing of components at molecular level. Also, they require lower synthesis temperatures compared to solid-state methods. Now let us move to characterization techniques. First, XRD, X-ray diffraction. This technique is used to detect exact lattice distortions and it confirms the crystal structure of the material. Next, SEM and TEM. These techniques help us visualize surface morphology, grain boundaries, and even atomic scale defects. Next, XPS and EPR. These are spectroscopic techniques used to identify oxidation states of elements and specific defect centers in the material. Finally, TGA, thermal gravimetric analysis. This technique measures weight loss when the material is heated. Using this, we can calculate the exact oxygen deficiency represented by delta. Now let us look at the flow diagram at the bottom. First, we take precursors. Then, grinding is done, followed by calcination, then pelletizing, and finally sintering. After these steps, we obtain the final defect perovskite material. So remember this sequence clearly because it is very important for exams. In the next slide, we will move to superconducting materials based on perovskites. Now let us begin a very important topic, high-temperature cuprate superconductors. First point. These materials were discovered in 1986, and this discovery was very significant because cuprates broke the strict limit of around 30 Kelvin, which was considered the maximum temperature for conventional BCS superconductors. Next point. Cuprates are a complex family of layered transition metal oxides. They are directly derived from the perovskite structure. Now, very important line. The defining physical feature of these materials is the CuO2 planes. These are two-dimensional sheets of copper atoms coordinated by oxygen atoms in a square planar arrangement. You must remember, superconductivity happens in these CuO2 planes. Now next, these active CuO2 planes are separated by spacer layers. These spacer layers contain rare earth or alkaline earth metals, and they act as charge reservoirs. That means they supply or control the number of charge carriers in the system. Next point. Undoped cuprates behave as anti-ferromagnetic insulators. This is quite unusual because classical band theory predicts that they should behave like metals. Now the most important concept. Superconductivity is induced only by doping. Doping means introducing holes or electrons into the CuO2 planes. This injection of charge carriers enables superconductivity. Now look at the diagram on the right side. You can clearly see the layered structure. The CuO2 planes are shown as flat sheets, and superconductivity occurs in these layers. Between them, there are charge reservoir layers that support the system. So remember this key idea. CuO2 planes are the heart of superconductivity, and doping is the key to activate it. In the next slide, we will study a specific example, YbCO superconductor. Now let us understand a very important example of high-temperature superconductors, YbCO. First point. YbCO, yttrium barium copper oxide, is known as the famous 123 compound. It is called 123 because of the atomic ratio of yttrium, barium and copper. Now the most important breakthrough. The critical temperature Tc is approximately 92 Kelvin. This is very significant because it is higher than the boiling point of liquid nitrogen, which is 77 Kelvin. This makes the material practical and economical for real applications. Next point. When the material is cooled below the critical temperature Tc, its electrical resistance suddenly drops to zero. This means the material becomes a perfect conductor. Now next concept. YbCO shows the Meissner effect. This means it behaves as a perfect diamagnet and completely expels the applied magnetic field from its interior. Now next line. The mechanism of superconductivity in YBCO is non-conventional. It arises due to strong electron correlations and magnetic interactions within the CuO2 planes. Now very important point to remember, oxygen content represented by X is directly proportional to the critical temperature Tc. This means if oxygen content changes, Tc also changes. Now look at the graph on the right side. You can see resistivity plotted against temperature. As temperature decreases and reaches Tc, there is a sharp drop in resistivity to zero. This point is called the superconducting transition. So remember this key idea. YbCO becomes superconducting below 92 Kelvin, and oxygen content plays a crucial role in its behavior. In the next slide, we will compare different cuprate systems. Now let us understand the comparison between two important cuprate systems, the 123 system and the 214 system. First point. Both of these systems are prepared using high-temperature solid-state methods. This includes calcination and sintering of metal oxides or carbonates. Next point. Both systems depend strongly on the CuO2 planes for superconductivity. However, they differ significantly in their structure and doping mechanisms. Now let us compare them one by one. First, 123 system, also known as YbCO. Its chemical formula is yttrium barium copper oxide 7-X. The critical temperature Tc is approximately 92 Kelvin. This is very significant because it is higher than the boiling point of liquid nitrogen, which is 77 Kelvin. Next point. It has a layered orthorhombic structure. It contains two-dimensional CuO2 planes and also one-dimensional copper-oxygen chains. These copper-oxygen chains play an important role in charge transport. Now doping. In YbCO, oxygen annealing is very important. The oxygen content directly affects superconductivity. If oxygen is lost, the material can become a non-superconducting tetragonal phase. Now let us move to the second system, 214 system, also known as LSCO. Its formula is lanthanum 2-X strontium X CuO4. The critical temperature here is around 35 Kelvin, so it is lower compared to YbCO. Now structure. It has a K2NiF4 type layered perovskite structure. It contains CuO2 planes but does not have one-dimensional copper-oxygen chains. Now doping. In this system, chemical substitution is required. Here, strontium ions replace lanthanum ions. This substitution introduces holes into the system which enables superconductivity. Now one important takeaway. The 123 system is more complex, but it gives a much higher critical temperature. In the next slide, we will study the normal state properties and anisotropy. Now let us understand normal state properties and anisotropy of cuprate superconductors. First point. Above the critical temperature Tc, cuprates behave as non-Fermi liquids. This means they do not follow the normal electron behavior predicted by classical metal band theory. Next point. Because of their layered two-dimensional structure, they show strong anisotropy in almost all physical properties. Anisotropy means the properties of the material depend on the direction in which they are measured. Now next concept. Conductivity along the AB plane, that is within the CuO2 layers, is much higher than conductivity along the C-axis, which is perpendicular to the layers. So electrons move easily within the layers but face difficulty moving between the layers. Next point. If we look at resistivity versus temperature, in the optimally doped region, it shows a perfectly linear relationship over a wide range of temperature. This behavior is quite unusual compared to normal metals. Now next important concept. In underdoped regions, a pseudo-gap phase appears above the critical temperature.
This means there is a partial reduction in the electronic density of states. In simple words, some electronic states become unavailable even before superconductivity begins. Now, final point. This leads to a very interesting behavior. Electrons start pre-pairing or showing correlated motion even before the material reaches zero resistance. Now look at the diagram on the right side. You can clearly see high structural anisotropy. The arrows indicate that electron movement is much easier along certain directions. So remember this key idea. Cuprates are highly anisotropic materials and their behavior is very different from conventional metals. In the next slide, we will study phonons and lattice vibrations. Now let us understand an important concept. Lattice vibrations, specifically acoustic and optical phonons. First point. Phonons are quantized units of lattice vibrations. This means vibrations in a crystal are not continuous but occur in discrete energy packets called phonons. These phonons play an important role in thermal transport and also in optical properties of materials. Now next, acoustic phonons. In this case, all atoms in the unit cell move together in the same direction. This motion is similar to a sound wave, so they are called acoustic phonons. Now next, optical phonons. Here, neighboring atoms vibrate in opposite directions. Because of this opposite motion, oscillating electric dipoles are created. This is a very important point. Now, in cuprates, optical phonons are mainly generated due to rapid stretching and bending of copper-oxygen bonds. This happens within the two-dimensional CuO2 planes. Next point. Oxygen atoms are very lightweight.
Next point. Oxygen atoms are very lightweight. Because of this, they can vibrate at very high frequencies. So, optical phonons in these materials have high frequency. Now, how do we study these phonons? They are studied using two important techniques. First, infrared spectroscopy, which involves absorption of radiation. Second, Raman spectroscopy, which involves scattering of light. Now, look at the diagrams at the bottom. In the acoustic mode, atoms move in the same direction. In the optical mode, atoms move in opposite directions, which creates an electric dipole. So, remember this key idea. Acoustic phonons are like sound waves, while optical phonons involve opposite motion and interact with light. In the next slide, we will study coherence length and its importance. Now, let us understand an important concept in superconductivity, coherence length denoted by Xi. First point. Coherence length is the spatial distance over which the Cooper pair wave function maintains a uniform phase. In simple words, it tells us how far the paired electrons remain connected or correlated in a superconductor. Next point. Basically, coherence length represents the physical size of a Cooper pair. Now, let us compare two cases. First, in conventional BCS superconductors, the coherence length is very large. It is of the order of hundreds of angstroms, which means Cooper pairs are spread over a large distance and overlap significantly. Now, second case. In cuprate superconductors, the coherence length is extremely short. It is only a few nanometers. This means the Cooper pairs are tightly bound and more localized. Next important point. Coherence length in cuprates is highly anisotropic. That means it depends on direction. The in-plane coherence length Xi AB is much larger than the out-of-plane coherence length Xi C. So, pairing is stronger within the CuO2 planes than between the layers. Now, final point. Because of this short coherence length, cuprates behave as type II superconductors. In type II superconductors, magnetic fields can penetrate the material in the form of quantized vortices. Now, look at the diagram on the right side. In BCS superconductors, you can see a large coherence length with overlapping wave functions. But in cuprates, the coherence length is short and the Cooper pairs are tightly bound. Also remember, because of short coherence length, cuprates are very sensitive to defects and grain boundaries. So, remember this key idea. Short coherence length leads to strong pairing but also higher sensitivity to structure. In the next slide, we will study thermal and elastic properties. Now, let us understand elastic constants, phonon lifetimes, and heat capacity in cuprate superconductors. First point. Elastic constants describe the stiffness of the lattice. In cuprates, atomic bonding is much stronger within the planes compared to the out-of-plane direction. This again shows anisotropy in the material. Now, next concept, phonon lifetimes. This means the time duration before a phonon decays. If phonon lifetime is long, thermal transport is very efficient. But defects in the material reduce the phonon lifetime significantly. Now, next important point, heat capacity denoted by CV. Heat capacity shows a very important behavior at the critical temperature Tc. It exhibits a sudden jump, which is called an anomaly. Now, understand this carefully. Above Tc, heat capacity changes smoothly with temperature. But exactly at Tc, there is a sharp discontinuity. This happens because electrons reorganize themselves and form Cooper pairs. Now, below Tc, the electronic contribution to heat capacity decreases exponentially. This is because electrons are now paired and locked in the superconducting state. As a result, lattice vibrations or phonons dominate the heat capacity. Now, look at the graph on the right side. You can clearly see a sharp peak at Tc. This peak represents the heat capacity anomaly. Now, very important exam point. This sudden jump in heat capacity is direct evidence for the opening of the superconducting energy gap. So, remember this key idea. Heat capacity behavior confirms superconductivity. In the next slide, we will study microwave absorption and multi-gap superconductivity. Now, let us understand microwave absorption and multi-gap structure in superconductors. First point. In superconductors, DC electrical resistance is exactly zero. However, when an AC field is applied, especially in the microwave region, a small amount of resistance is still observed. Next concept. Microwave absorption. This occurs due to two main reasons. First, the physical inertia of Cooper pairs. Second, the movement of magnetic flux vortices inside the material. Because of these effects, there is a slight energy loss when microwaves interact with the superconductor. Now, next point. By studying this surface resistance, scientists can accurately determine the size of the superconducting energy gap. This is very useful for understanding the internal electronic structure. Now, next concept. Multi-gap superconductivity. In some advanced cuprate materials, more than one energy gap exists at the same time. This means different groups of electrons behave differently. Now, final point. Because of this phenomenon, electrons from different electronic bands participate in superconductivity with different pairing strengths. This phenomenon can be studied using advanced techniques like ARPES. Now, look at the diagram on the left side. You can see a microwave AC field interacting with a YBCO sample. Inside the material, magnetic vortices oscillate, which leads to slight AC energy loss. So, remember this key idea. Even though superconductors have zero DC resistance, they show small losses in AC fields and can exhibit multiple energy gaps. In the next slide, we will understand the pairing mechanism in superconductors. Now, let us understand one of the most important concepts in superconductivity, the pairing mechanism in BCS theory and in cuprates. First point. All superconductivity requires electrons to overcome their natural repulsion and form what are called Cooper pairs. Now, let us first understand the conventional mechanism, that is BCS theory. In this theory, one electron moves through the lattice and distorts it by interacting with phonons. This distortion creates a temporary positive charge region. This positive region attracts another electron, leading to the formation of a Cooper pair. So here, pairing is mediated by lattice vibrations, that is phonons. Now, let us move to cuprates. Cuprates do not follow BCS theory. The phonon-mediated mechanism is too weak to explain their high temperatures above 90 Kelvin. So, a different mechanism is responsible. In cuprates, pairing is driven by very strong electron-electron interactions. Now, the most accepted idea. This pairing is mediated by magnetic spin fluctuations. These occur in the anti-magnetic background of the CuO2 planes. So, instead of lattice vibrations, magnetic interactions help electrons to pair. Now, very important note. The exact microscopic theory of high-temperature superconductivity is still not completely understood. It remains one of the biggest unsolved problems in physics. Now, look at the diagrams at the bottom. On the left side, you can see BCS pairing, where phonons mediate the interaction. On the right side, you can see cuprate pairing, where magnetic spin fluctuations play the key role. So, remember this key idea. BCS superconductors depend on phonons, while cuprates depend on strong correlations and magnetic interactions. With this, we complete the concept of superconductivity mechanisms.
Now let us understand the real-world applications of high-tech materials, especially superconductors and defect perovskites. First point, power transmission. Superconducting cables can carry very large currents with zero energy loss. This makes power transmission highly efficient. Next point, MRI and maglev applications. Superconducting magnets produce very strong and stable magnetic fields. These are used in MRI machines for medical imaging and in maglev trains for frictionless movement. Now, next important application. SQUID sensors. SQUID stands for Superconducting Quantum Interference Devices. These are the most sensitive magnetic field detectors available. They are used in applications like brain imaging and advanced research. Next, energy applications, especially solid oxide fuel cells or SOFCs. Defect perovskites, due to their high ionic conductivity, act as excellent cathode materials in fuel cells. Now, next, microwave devices. Cuprate superconductors are used in high-performance telecom filters and satellite communication systems. Now, final point. All these applications are possible because of the interaction between atomic-level defects and quantum mechanical effects. This combination is driving modern technological advancements. Now, look at the images on the right side. You can see examples like zero-loss power cables, MRI scanner, and maglev train. These clearly show how fundamental chemistry concepts are applied in real-life technologies. So, remember this key idea. High-tech materials are not just theoretical concepts. They are directly used in advanced technologies. This completes our topic on defect perovskites and high TC superconductors. Hello.